All right, so now let's practice here a situation where we're charging by induction. We have a neutral metal sphere, and we're going to bring a negatively charged object close to the sphere, and we are going to ground the sphere. And if you remember, grounding is providing a pathway. Sometimes the symbol looks like this, where you provide a pathway for electrons to either come on or go off. And so since this is a review, let's see if you guys can work through the next three pictures. You know, this one is where we ground it, and then after that we take the grounding away, and then here we take the balloon away. And yeah, let's see if you can try see if you can do that. So again, it's not going to touch, right? It's just going to be close to it, and then we're going to ground it. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we ground it, provide a pathway for the electrons to come off, and the sphere becomes positively charged. And so remember, the fact that it's positively charged doesn't mean that there are, any less or more atoms. It's just the fact that, some of those electrons have left, and now we've got a positively charged sphere. All right, so let's try this one now. Let's say we bring a glass object, glass charged, or a positively charged object towards this neutral sphere. And yeah, let's you can go ahead and pause the clip and give this one a try, and what will happen if we ground this one and we charge it. So go ahead and pause the clip and give it a try, and when you're ready to check, you can hit play to continue. Okay, so we ground it, and we're providing a pathway, and it turns out electrons are going to come on, and then we unground it, and the whole thing becomes negatively charged because we, provided that pathway there, and now the whole sphere is equally negatively charged. And that again means that the same number of atoms, but those atoms have more electrons, and it's an unbalanced situation. All right, so this is a good one to practice looking at positive charge as well as looking at how moles work. And so this will be a good chance to practice this here with this. And so we have 3 moles of hydrogen gas, and we want to figure out how much positive charge is in there. And so yeah, go ahead, and if you feel like you can go all the way through, go ahead and pause the clip and try it. If not, I'll give you some more intuition. All right, so H2, this is hydrogen here. You have a proton and an electron. That's it. Now H2 means that you have 2 protons separated out, and they are sharing electrons. So these electrons are flying around. They're being shared between these, okay? And therefore, if we have 3 moles, here's 1 mole. If you have 1 mole of hydrogen gas, that means that you have this in here. And how many of those do you have? Well, here's our constant. We have 6.02 times 10 to the 23rd molecules of H2 in a mole. So that means you have that many atoms. You have that many of these things, right? So therefore, if you have 3 of them, we're going to have to multiply this by 3. Then each of them has 2 protons, so we'll take that number, multiply it by 2, and then that's the number of protons. Then once we know the number of protons, we multiply that by the charge of a proton, and you can find that on your equation sheet, and then get how much charge you have. So yeah, go ahead and pause the clip and finish it up, and when you're ready to check, you can hit play to continue. All right, so we'll multiply that by the charge, which is 1.602 times 10 to the negative 19th, and we'll get a total positive charge of positive 5.786 times 10 to the 5th coulombs. And for negative charge, negative 5.786 times 10 to the 5th coulombs. So the net charge will be 0. We'll have an equal number of electrons as we do protons, and therefore the net charge is 0 when we add them up. All right, so this is a good one to practice here, where we have a mass that is suspended in air. B is suspended in air, and it's being attracted by the positive charge up top, and it is negatively charged down here. And what we want to find out is if it's suspended in midair, meaning it's just sitting there, what's the mass of this ball then? And so, yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so we know that there's a force of attraction between these two according to Coulomb's law, which is K Q1 Q2 over R squared, electrostatic attraction. And then you have the force of gravity, mg, holding it down. And those are balanced. If we did the sum of the forces in the y equals ma in the y, we have the positive force, the Coulomb of, we'll just use Fa here, but the Coulomb force, which is, the electrostatic force, plus the negative force of gravity equals 0, because the acceleration is 0. It's just suspended there. So they're going to be equal to each other, and therefore we'll get a mass not very big, 4.07 times 10 to the negative 10th kilograms. And that should kind of make sense, because if you've got those two separated out by 1.3 meters, we've got our charges here. And yeah, it's not going to be able to hold up very much mass. All right, so now we are ready to practice force on multiple charges. And this is a good opportunity to do that here. We have 3 charges. Let's call the one on the left Q1, the one in the middle Q2, and the one on the right Q3. And what we talked about today in review was with the if we want to just find out what the force is on a 4 microcoulomb charge, then what we do is we, and again, this is positively charged here, negatively charged here. What we do is we just concentrate on 2 of them. So we say, okay, how does Q3 feel? How is it forced by Q2? And we forget that Q1's there. We just ignore it. And so we know Q3 is going to be pushed to the right by Q2 because they're like charges. So when we calculate this, we're going to get blank newtons to the right. So the force on charge 3 due to charge 2 is KQ3Q2 over R squared. And then we'll get our answer, and it's going to be blank newtons to the right. So yeah, go ahead and do that, and then we'll go from there. So go ahead and pause the clip and do that, and then we'll go do the next step. All right, so we should get 0.072 newtons to the right. Now the next step is to say, okay, how is Q3 affected by Q1? And then we forget that Q2 is there. Well, Q3 is going to be attracted to Q1. And we don't care what happens to Q1. All we care about is Q3. How does that feel? So when we calculate this one, the force on Q3 due to charge 1, Q1 is KQ3Q1 over R squared. And we're going to get blank newtons to the left when we calculate that. And so therefore, really, the 2 forces are fighting each other. So when we add them up, one's going to be negative, the other's going to be positive. And we'll get a difference there. So yeah, go ahead and pause the clip and give us a try. And when you're ready to check, you can hit play to continue. Okay, so 0.027 newtons to the left. And when we add them up, we'll get the total positive 0.072 to the right plus negative 0.027 to the left. And we'll get a total of 0.045. And that's what Q3 is going to feel. That's that 4 microcoulomb charge. All right, so now we're ready to practice 2 dimensions. Let's call the charge down here Q2. It's positive. Q1 is positive, and then Q3 is negative up here. And we do a similar process here where we pretend like the other one's not there and work it out. Now, the easiest way probably to do this is to say, okay, well, let's just pretend this one's not here. How does Q2 feel based on Q1? Well, they're like charges. It's going to be pushed away. So the force on charge 2 due to charge 1 is KQ1 Q2 over R squared. And again, you don't need to worry about the order here because you're just multiplying those. Now we're going to get blank newtons to the right due to that in the positive x. Now, that step's pretty straightforward, so let's do that first. Go ahead and pause the clip, calculate that, and then we'll move from there. All right, so we should get 0.072 newtons to the right. Now what we're going to do is we're going to ignore Q1. We're going to say, okay, that doesn't exist now. How is Q2, which is positively charged, how does Q2 feel as a result of Q3, which is negatively charged? Well, there's going to be a force and an angle like this, and it's going to be pulled up. Now, that gets a little complicated because you're going to have a force and an angle. So when you calculate that, you're going to get blank newtons. Well, what we got to do is we got to break that up into the x and the y components. The x and the y components. So, we've got a, we'll have the angle here. We can break this up and figure out what that is, Now, this is going to be negative here, whatever blank newtons, or we could just say to the left. And then we're going to have these up, or in the positive, right? Now, once we get those, we can bring those together. So go ahead and do that step, and then when you're ready to check, you can hit play to continue. All right, so we should get for that force, 1 squared plus 1 squared equals c squared, and then we get the radius squared, and we should get 0.054 newtons, 45 degrees above the x-axis. And then when we break it up into the x and y components, we should get 0.03818 for each of those. Now, what we have to do is get the total x, total y. Now, the first one was to the right, but this one is to the left. So when we add those up, you got to keep the signs, perspective, then you'll have your total y. Once you get your total x, total y, you can draw your coordinate axis and then do vector addition of those two and then get the resultant. So yeah, go ahead and pause the clip and finish this out. And when you're ready to check, you can hit play to continue. Okay, so 0.0338 newtons. For the x total, for the y total, 0.03818. There's only one y force, and we should get a total of 0.051 newtons at 48.5 degrees above the positive x-axis would be the force on this charge, and that's the superposition of those two. All right, so now we're ready to practice some field lines, and if you remember, these are two positively charged spheres, or well, positive on the right, negative on the left, and we'll say they're equally charged. We talked about today how, we reminded ourselves how we do this, right? So if we have a proton, a test charge, we place it in there, and then we see where it goes, and that will tell us what the field does. And so, for instance, we place a positive test charge here and see where it goes. It's going to go straight over. And that's how we draw the field lines. And so, now the protons aren't actually there, right? But if they were there, they'll tell us where the field is, and the field is invisible there. They're also called lines of force. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so we've got that one going there. This one being forced up and around. This one being forced down and around. This one would be coming up and over. And yeah, you guys get kind of the pattern. Now, we also talked about how if you have more lines, that indicates a stronger field. And so the more lines that you have, for instance, if we filled this in with more lines, like one coming here, one coming here, one coming here, we could even draw more lines, one coming around here. That's just showing that these charges have a lot of charge and that the field's strong. If you only have a few, it doesn't mean, it means that you don't have as many, okay? All right, so let's go ahead and practice this one here. We have a proton that's traveling into a field, and it enters the uniform field. The uniform field is 5,400 newtons per coulomb, and it's directed in the positive y direction here, and we want to find the acceleration on the proton. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. I encourage you to use your equation sheet here. See if you can remember how this works. Okay, so force is the EQ. I think on your equation sheet, it's got it in the form of E is force over Q, and so we can find the force on it. So 8.64 times 10 to the negative 4 or negative 16 newtons to the north, and so F equals ma. We've got the mass on our equation sheet. We've got the force, so the acceleration on this would be 5.18 times 10 to the 11th meters per second squared.